This video demonstrates the use of Duke's Immersive Virtual Environment, DIVE, to generate lifelike fear conditioning data in humans. Virtual worlds are created with Virtual software, and code is generated to elicit stimuli presentations. The participant is set up with electrodes for skin conductance recording and wrist stimulation, as well as button presses, within the virtual reality setting. Skin conductance response and button press data are then collected, while dynamic stimuli are presented in the DIVE. Physiological data and expectancy measures are analysed to demonstrate fear acquisition, fear extinction, and fear memory retention to conditioned stimuli or contexts.
Hi, I'm Kevin Labar. I'm a professor at the Center for Cognitive Neuroscience at Duke University.
I am Rachel Brady, Director of the Duke Immersive Virtual Environment.
Hi, my name is Nicole Huff. I'm a postdoctoral associate in Dr. Labar's laboratory.
Hello, my name is David Zielinski from the Visualization Technology Group.
Today, we will show you a procedure for conducting human fear conditioning experiments using fully immersive, three-dimensional virtual reality.
We use this procedure to examine contextual influences on fear acquisition and memory retention.
So let's get started.
To examine contextual influences on fear acquisition and memory, human participants are presented with dynamic conditioned stimuli in a fully immersive virtual environment known as Duke's Immersive Virtual Environment. The DIVE system consists of a 3 meter by 3 meter by 3 meter room in which all four walls, the ceiling, and the floor show stereographic computer images by rear projection. Each wall has its own DLP projector, which in turn is controlled by a dedicated computer. One of the walls slides open to allow access into and out of the DIVE. There is a tracking system that provides 3D location and orientation information for the participant's head and hand positions. Active stereographic vision is provided through liquid crystal shutter glasses worn by participants. The 6 wall-dedicated computers are controlled by a master computer that communicates to the tracking system, controls the sound system, and controls an electrical shock system, which is used for fear conditioning. The 7 computers are synchronized on image frame boundaries through the GenLock capability of their NVIDIA graphics cards. Navigation through the virtual environment is limited to a fixed path that is identical in all virtual worlds. Movement along this path is controlled through the Virtuals software system. Virtuals communicates with the tracking system through the Virtual Reality Peripheral Network, an open source library. VRPM registers the participant's head and hand location and orientation, as well as button press information. Virtuals uses the head tracking information to render the 3D scene at the correct perspective for the participant. Now let's see how to set up a participant for a fear conditioning experiment within the DIVE system. During fear conditioning experiments inside the DIVE, participants encounter dynamic conditioned stimuli consisting of snakes and spiders paired with electrical wrist stimulation. Before starting the conditioning procedure, first randomly assign each participant to a particular conditioned stimulus, termed the CS Plus stimulus, consisting of either snake images or spider images. For all participants, the unconditioned stimulus to be paired with the CS Plus stimulus consists of electrical stimulation of the wrist. For each participant, the stimulus that was not selected to be the CS Plus serves as a control and is termed the CS Minus stimulus. Now randomly assign the participant a particular virtual context in which he or she will view the stimuli. One possible virtual reality context consists of an indoor environment, and the other context consists of an outdoor environment. To set up the electrical stimulation that will be paired with the CS Plus stimulus, apply a small amount of conductive Signagel onto the electrodes, then secure a bipolar surface stimulation electrode over the median nerve of the participant's dominant wrist. Secure the electrode leads by a rubber strap and attach them to a Grass Telefactor SD9 stimulator. Now to find the appropriate stimulation voltage. Start with the voltage set at a low level of 30 volts and stimulate for 200 milliseconds at 30 to 50 Hz, increasing the voltage in increments of 5 volts until the participant indicates that their tolerance level has been reached without inducing pain. The goal is to find a setting that is perceived as highly annoying but not painful. The dependent measure of fear in human participants during this experiment is the skin conductance response. Participants should first wash and dry their hands while they wait at least 10 minutes to acclimate to the temperature of the building. Before attaching the SCR electrodes, exfoliate the middle phalanges of the first and second digits of the non-dominant hand with Nu-Prep. Wipe them dry, and then apply a small amount of Signa conductive gel in the electrode. Now to measure SCR, attach silver-silver chloride electrode discs to the middle phalanges of the first and second digits of the non-dominant hand. The leads reach a BioPack physiological recording system located just outside the DIVE in the control room. The BioPack system synchronizes with the stimulus presentation computer running Virtual's software. With the electrical stimulus and SCR electrode set up, seat the participant in the center of the dive, facing forward, with head tracking on the 3D eyeglasses. In the dominant hand, place the wand device, which will record button press responses from the participant when they encounter a snake or spider. Now inform the participant that their task is to indicate with a button press on the wand how likely they think it is that they will receive electrical stimulation when encountering a snake or spider. The buttons are ordered from left to right, left being least likely to receive stimulation. Remind them that the button press does not influence the occurrence of electrical stimulation. Now let's see the fear conditioning experiment. The fear conditioning experiment is conducted over 2 sessions separated by 24 hours. The first session consists of an initial habituation period immediately followed by the fear acquisition phase. The second session consists of memory retention testing and extinction training. During the initial habituation period, present the participant with 4 trials of each CS type viewed on a grey background in 3D full immersion but without reinforcement or the virtual world in which training or testing will occur. In each trial, the stimulus appears for 4 seconds and co-occurs with a rattle or tapping sound to signal the appearance of a snake or spider. This phase allows for acclimation to the experimental environment in the DIVE and reduction of orienting responses to the conditioned stimuli. Immediately following the habituation phase, begin the fear acquisition phase. Present 16 intermixed trials of each CS type, in which the CS- is presented alone, and 5 of the 16 CS Plus trials are reinforced with electrical stimulation. Approximately 24 hours later, begin the second session. In this phase, present the participant with 16 trials of each CS type with no electrical stimulation in a virtual context that is either the same as or different from the fear acquisition context, depending on which group the participant was initially assigned to. The task and instructions to the participant are the same as at the second session. Now we'll show some results from fear conditioning experiments in the DIVE. Equivalent within-session fear acquisition and extinction across groups was found, indicating that reliable and informative fear conditioning studies can be performed within the constraints and capabilities of a fully immersive environment. Moreover, in participants who remained in the same context for days 1 and 2 of the experiment, there was robust contextual fear memory relative to those who experienced a context shift. The retention of fear is stronger in the DIVE than in a conventional laboratory-matched paradigm.
We've just shown you how to conduct human fear conditioning experiments using fully immersive virtual reality. This technology is useful for examining contextual influences over fear memory.
And remember, when conducting these experiments, it's important to constrain the capabilities of virtual reality so that you can generate interpretable data. For example, you want to control how much a participant moves, as well as placement and duration of stimuli.
So that's it. Thanks for watching and good luck with your experiments.